we're asked to find the volume of this region rotated around the y-axis. So if you do it with the washer method, you're going to be integrating parallel to the axis of revolution. So this is going to be in terms of y. And so the washer method would be finding the bigger radius. So that would be this entire region from the y-axis to this outer bound over here. And then we're going to subtract that by this region when it's revolved around the y-axis. When you do, you're going to be left with just this region. Okay. And then cylindrical shells would be when you integrate perpendicular to the axis of revolution. So that would be in terms of x. So with cylindrical shells, you're going to need to come up with the equation of the region when it is when come up with the equation for the right cylinders for this region. So that would look like this. That's one right cylinder, and then we have another right cylinder that come on later on in the integration because we're in terms of x. So here would be another right cylinder. Okay, so I'll do both methods. So if we do it through the washer method, we are going to integrate with respect to y. So this is starting at y equals 0. And then to find the endpoint, you would want to plug in x equals 3 to find out this y value, to find out where they intersect, right, where these two lines intersect. So it's going to end at square root of 3. That's the ending y value. And the biggest region that we talked about is a constant radius all the way through. So it's pi 3 squared. And then we need to subtract that by the smaller radius. So we need this distance on the x-axis. So if we rewrite this equation, this is going to be x equals y squared. So if you plug in a value for y into this equation, it's always going to tell you where you are on the x-axis. So y equals 0, x is 0, right? This has a radius of 0. If y equals 1, then x equals 1. And that looks to be just about the radius according to our drawing. So it's pi. The radius is always, it's this x distance, so it's defined by y squared. And then we can do that integration. So this is from 0 to 3. So it's 9. Here, and I'll factor out the pi from both these terms. So it's 9 minus y to the 4th dy. So integrating term by term, we're going to get 9y minus y to the 5th over 5 from, oh, that's square root of 3. Sorry about that. So that's pi times 9 square roots of 3 minus square root of 3 to the 5th. So that's going to be 3 to the 5 halves over 5. We get common denominators. Let's see if I can make that any cleaner too. I don't know if I can. That's pi. If I get common denominators, that's 5 in the denominators. That's 45 square roots of 3 over 5 minus 3 5 halves over 5. So you could factor out, that's 45 square roots of 3. That's 1 minus, I'm factoring out a 3 to the 1/2 power, so that's going to be 3 squared here. So that's 1 minus 9, 45. This is not my favorite part of this calculus course, is all this algebra. I'm worried I did it wrong too. What did I miss? Factored out a square root of 3. Oh, but I can't factor that out of both. Shoot, so I gotta back up. I did mess something up. Let's leave it here. We'll see if we get something similar with this other question. Okay, because this would be 45 square roots of 3 minus 3 to the 5 halves all over 5. And you could do a little bit more factoring. I don't know if that's going to make it much neater though. Okay, so doing it with the washer method, we need to come up with the equation of every type of right cylinder as we integrate with respect to x here. Okay, so these right cylinders, again, here's the drawing I made before of just one of those infinite amounts of right cylinders we're making. Okay. We need the height of each right cylinder. That's dictated by the y value, right? So we get the y value by taking the square root of x each time. So we're doing this, it's 2 times pi times r, which is x, right? X every time, so r is x. And then our height is going to be square root of x every time. And then the limits of integration starts at x equals 0, ends at x equals 3. So before we integrate, this is 2 pi x to the 3 halves, because x to the first times x to the 1 half makes x to the 3 halves when we add those. So now integrating, we get 2 pi, that's going to be x to the 5 halves, so we're going to multiply that by 2/5, x to the 5 halves, from 0 to 3. So plugging in limits of integration, the only one that really matters is that top one, plugging in that 3. So we're gonna have 4 pi over 5 times 3 to the 5 halves. So it depends on which method you're more comfortable with. Both these answers are the same. This is the part where I just I just froze on the algebra. We can rewrite this to turn into this. Here, maybe I'll do that at the end of the video. Let's just answer the question with the easier form. It says find the value of a when the answer is a times pi over b. So if I rewrite a little bit more, that's 4 times 3 5 halves pi over b. So this is our a. So I'm not sure who made the original question. It wasn't me, but it's weird to do that when you have a fractional exponent. This is 3 to the 2.5 power times 4. So it looks like a is 62.35. It's not an integer. Okay, so you can stop the video now if you want. If you're comfortable with both those approaches, I'm just going to fiddle with the algebra to get this to match this form. Okay, so that's pi 45 square root of 3 minus, look, this is square root of 3 times 3 squared. That's the same thing over here. So I can factor out a square root of 3. That's 9, so I can factor out a 9 from the numerator too. So 9 square root of 3 pi. The numerator is going to be 5 minus 1, right? Yeah, that's 4. Okay, so that's just going to be 4 over. So 4 times 9. Oh, here, actually, to get it in the same form, 5 minus 1 is 4. 9 is 3 squared, so 3 squared times square root of 3 is 3 to the 5 halves again. Still got pi. It's over 5. Okay, I did it. I was able to take this, turn it back into that form.